In this video, we'll discuss analog to digital conversion, or ADCs. We'll discuss some of the important parameters and requirements when using ADCs, and we'll also look at how to use the ADC peripheral that's on our particular microcontroller, the MSP432. But before we get into those details, let's first talk about why analog is so important for embedded systems. Remember that embedded systems are usually very tightly coupled with other physical components in the physical world, and everything in the physical world is an analog signal. So for many embedded applications, one common thing that needs to be done is to take or measure these analog signals and convert them into electrical signals that can be processed and actuated on with our microcontroller. Now there are many different types of sensors and devices that can do this. Broadly speaking, many of these devices are what we call transducers, devices that take one type of energy and convert it into another. And this could be electromechanical, photonic, or even electrical. Things like thermocouples, accelerometers, are examples of these devices. So the transducer converts some physical phenomenon to a voltage, and it's going to do this in some well-defined way. So when we look up the datasheet for a particular sensor, we're going to find what the relationship is between that physical phenomenon, for example, temperature, as shown here on the x-axis, and the corresponding voltage, shown on the y-axis. This is important because then we can use this inside our microcontroller to interpret the measurements in our system and the quantities of the physical phenomenon. Another simple example is using a simple photocell to measure the light within a room. But there are many other sensing applications, including some that are digital. Things like force, sound, position, acceleration, location, electric fields are all really common physical phenomena that many embedded systems may need to measure and act on. So how do we get from the analog to the digital world? Well, what we'd like is to have this sort of black box where we have the physical phenomenon, and on the output, we can get the actual engineering units or whatever that phenomenon is. But to get there, we're going to have to do some conversions and calculations. So the physical phenomenon will be converted into a voltage or a current by a sensor or transducer. And then we're going to use an analog to digital converter, which is typically a discrete component or an integrated peripheral on the microcontroller, to convert that voltage to a digital value, or we can also call this an ADC count. Then in software, we can interpret this digital value and convert this into the engineering units that our application bases its logic on. And so how do we represent an analog signal digitally? Because remember, an analog signal is also continuous in time and magnitude. And so the way that we typically do this is to take samples, and we'll represent the analog signal as a time series of discrete values. So our microcontroller will read the ADC periodically to create this time series. And the frequency of the sampling, or that period between samples, is a key parameter, which we'll talk some more about in a second. One of the first important parameters that we have to decide on when using ADC is the range. If we choose a range too small, we're going to end up clipping our signal and losing information above and below our maximum and minimum reference voltages. If we choose a range too large, we're going to lose some accuracy, not being able to represent the smaller range of values. The ideal range will be somewhere in between, sort of like the three bears and Goldilocks. We'd like it to be just right with the max and the min just below and above our reference voltages. Another really important parameter for ADCs, which we've also seen before with digital analog converters, is the resolution, or the number of discrete values that can be represented in that range. For the MSP432, we have a 12-bit ADC, so we can represent 4096 values. We've also talked about how the LSB, or the least significant bit, is an important parameter for the ADC or DAC. And this is because of quantization error. When we take in an analog value, the ADC is going to have to put it in one bucket, one discrete value. The larger that step size, the larger the quantization error. So obviously, more bits of resolution will give us greater information content with less error, but will also come at the cost of energy and performance. 10 to 16-bit ADCs are today a common resolution found with microcontrollers. Now, if you look up in the datasheet for the ADC, you're going to find an equation, just like we did for the DAC, for how to convert between the digital value, the ADC count, and the voltage. And it looks something like this. So we take the ratio of the input voltage minus the lower reference voltage over the total range times the number of total discrete values. And this gives us our ADC count. We can also do a little algebra and reverse this equation to calculate what the corresponding analog voltage input is, given a discrete value we've read from the output of our ADC. With this analog voltage then, and the knowledge we have on the datasheet for a particular sensor, say a temperature sensor, as we saw earlier and had a linear relationship, we can then calculate what the corresponding temperature is for that analog voltage which we read from the temperature sensor. Now, we do have to be careful though, because you might say, well, let's write some C code that looks like this to implement those equations. The ADC count divided by 4095 times 1.5. And if you write something like this, you might be surprised when you get a temperature C that is always 0. And this is because of the way that rounding occurs with integers in C. We need to be careful about underflow and overflow with these fixed point operations. In many cases, floating point operations would be too costly for a low power microcontroller that we're using. So in addition to the range, choosing the reference voltages for ADC, another really important parameter for using ADCs is the sampling rate. Again, we want to pick the right value for our sampling frequency, because if we sample too little, then we're not going to be able to reconstruct the signal that we care about, and we won't be able to actually accurately measure the signal. But if we sample too frequently, we're going to waste a lot of energy, a lot of computational resources and memory, which is also likely not going to be ideal. Okay, so an important concept that hopefully you've all seen before then that we can use to choose a good sampling frequency is the Nyquist theorem. In fact, we typically call this sampling at the Nyquist rate when we pick a sampling frequency based on the Nyquist theorem. And the basic idea is this, that if we sample at a frequency twice whatever the maximum frequency is and our input signal, we'll be able to completely reconstruct our signal without any aliasing errors. So as an example, if we have a 200 hertz signal sampled at 2000 hertz, we'd be able to get something like this, where our blue dots are the discrete samples and the solid blue line is the actual signal. So in this case, we can obviously see and interpret that this is a 200 hertz signal. But if we tried to sample at 2000 hertz a 1000 hertz signal, we get something like this, which is obviously not the case. So when the digital values might lead us to believe that it's just a constant signal. And even worse, we might get aliasing such as this. So if we're sampling at 2000 hertz and it's a 2200 hertz signal, the digital values seem to suggest that we do have an oscillating signal here, but it's the wrong frequency. And this is the idea of aliasing. Okay, so now let's talk about the actual ADC circuit and how we implement analog to digital conversion. There are different ways that ADCs can be built, but let's talk about one of the most common ways that ADCs are implemented, and that is with a successive approximation approach. The analog voltage is input into the ADC and then typically put into a sample and hold circuit, which is then connected into a comparator where we compare the sampled analog input with a sequence of different potential analog values which are generated with the rest of the circuit. So the successive approximation ADC will go through a sequence of test values represented in a register or the successive approximation register, and these digital values are converted into analog through a DAC, similar to as we've seen before. So this is the actual ADC on the MSP432, and we see that there are several important subsystems here, each with several software configurable options for the ADC. So on the left here we have the analog input, which can be connected to come from different ports on the chip as well as internal signals. So we have a large mux here, so select that. And this feeds into the actual ADC, which is shown in the block here at the center. The reference voltages are also configurable, and we can select these. The range for our signals, remember this is an important parameter for the ADC, as well as the clock rates. And there are two important clocks that we have to set. One is the internal clock rate for the ADC, as it steps through and compare the voltages with the analog input, as well as the actual sampling frequency, because this ADC also has the ability to be set up and take multiple samples and store this in its own ADC memory. Sort of like the timer A module is a counter with some additional logic that allows it to be set up and run on its own in order to complete some important functions like PWM signals. So the ADC has a memory for storing the actual data as well as control signals depending on how those samples and the pattern of the sampling from the ADC is supposed to happen. So just like we saw with the timer hardware and software, we're going to set up the ADC and configure all these parameters, the internal ADC clock frequency, the sampling frequency, the reference voltages, the input, the clocks. And then finally, the last thing we'll do is in software set a bit that actually starts and initiates the ADC to start sampling. We'll then in software have an interrupt generated when a sample is taken, and then inside that interrupt we can read that data and do whatever processing we need on it. Finally, I've also posted some sample code on Canvas that you can use for getting started on the ADC assignment.